the record. Okay. Thank you. Okay, so this is a problem from this reference, and this reference is basically a Biswas et al. It's a 2004 paper, and it's from Journal of Fluid Engineering. It's the topmost journal of the research field. So everybody who is starting their CFD, they start with some problems like aerofoil simulation, like the pipe flow, like the flow over the flat plate. This is another problem, which is the flow over the backward facing step. And these people have this case CFD, and the second reference, which is basically is a master reference, and the Biswas et al. They also use this reference as the geometry. Good. That's good. This person, which is Armele, is a person who experimentally solved this case in 1983. This geometry is the same as used in the both references, but I took the picture from this reference. Okay. So case.
Boş. Elin parasını sayesinin üstünde. Karışındır ya da cence diye çalışıyor. Ne çalışılır da bak. Onlar ikiden emeklilik diye bir şey yapmıyor diye ama. Bir de bir şey emekliyim de ben çalışıyorum.
Okay. So actually this flow in this case for this paper they have the cases they consider the laminar flow as well as they consider the laminar flow. But we are just following the laminar separation and reattachment. So the flow is laminar, it's stepping at this location, then it's again attaching at this location. The location varies. This may be over here or this may be over here. It depends on the Reynolds number. So as Reynolds number is increasing, the flow is reaching at a later point in the geometry part. So higher the Reynolds number, the higher the length of the reattachment of the flow. In this paper, you can see that they have told that the flow becomes three-dimensional after the Reynolds number of the 400. So from this reference, you can see that have determined experimentally that after the 400 Reynolds number, the flow becomes three-dimensional turbulent flow. So in order to solve the flow as a laminar flow, I kept the Reynolds number less than the 400. So deliberate tried I want to solve this flow, I want to simplify the flow. So that's why I chose the Reynolds number which is less than the 100. And they chose the three expansion ratios. This is the H by H expansion ratio basically. Three expansion ratios 1.9423 to 2.5. I use this one for this case. You can use these two cases also. So the expansion ratio basically is a ratio of the. You can divide this in two parts. This upper, the lower part. Okay. The height of the lower part is the capital H, and height of the upper channel is the small h. And ratio is known as the expansion ratio. Okay. So the ratio is 1.9423, and the Reynolds number is 100. This is my choice of these parameters. You can use other parameters. You can choose other things to solve the case. All the results are given in the paper. You can compare results with the paper, and you can see okay how accuracy you have done your CFD. Okay. I would suggest that you can talk and you can turn on your mic and then you can talk, and then again you can mute your voice. Okay, that's good. Issues? No problem. So basically we are building the case for this problem. So at the given conditions, for the given this condition which we chose from the paper, the reattachment wavelength is 2.70584 meters after the step. So this 2.70584. So for these conditions, this is the length which we are going to target in CFD. In our CFD, the results are close to this one, then we have the solution accuracy. Otherwise, we are off from the solution. So we will try to compare the result with the result, and we can believe our result that how accuracy we have in our CFD. Okay, so for this case, now we want to the important is that from this simple paper, which is a complex for us, I determine the main geometric parameters, main flow parameters, and main properties like density, viscosity, velocity, the length of each part of the channel. So what should be the length of this part? What should be this length? What should be this length? The step height. All things we have to determine from these conditions. Okay. So as we know that we chose the Reynolds number equal to 100 and the A by H is equal to 0.9423. And from figure you can see that this capital H is equal to the small h, which is the height of the channel upstream before this step, and the height of this step. This is equal to H is equal to H plus S. So let's assume that the small is equal to 1 meter. Now this is our arbitrary choice. You can choose the 2 meters, but that should remain same. As far as the Reynolds number is same, expansion ratio is the same, the result should be the same. Okay, I would suggest that you turn off your mic. Okay. Can I turn off your mic if you don't mind? Okay, thank you. Okay, so we have the Reynolds number 100 and the H by H is equal to 1.9423. So we chose the H is equal to 1 meter. It's an arbitrary choice, but it does not make any difference as far as this Reynolds number is same and the exponential ratio is the same. So you can choose the 2 meters, and in that case you will have some different H, the capital H value. So I thought it's simple to play in the units. So the small h is 1 meter, and from this equation we have the capital H is equal to into 1.9423 equal to the 1.9423, and from this equation because we know the H and H, small h and the capital H, so we can find out the value of S. So S is equal to capital H minus small h is equal to 0.9423. So now we have some parameters. So the small h is 1 meter, capital H is 1.9423, and the step height is the 0.3. Now you can see that we are getting the somewhere, and we are getting some geometric parameter. Okay, from the Reynolds number, which is by definition is equal to the number is equal to the density, the bulk velocity, and the diameter is the characteristic length. So in the case of the aerofoil, it's the call length, and any parameter which does not change with your flow conditions. So diameter is something which is constant. So 5 flows, the diameter is taken as instead of the length, and the viscosity here. So value we chose for the Nernst number is 100. So just keep in mind this thing. So let's assume that this velocity is equal to, so one parameter is decided. Nernst number is already fixed, and assume that the velocity is equal to 1000. This is also fixed. Next thing is diameter. This diameter is basically is a hydraulic diameter. Hydraulic diameter is the diameter by direction where the flow is passing. So it's basically approximation, like for cylindrical pipes we have the diameter equal to d. So what is the equivalent diameter in the case of some other shapes which are not circular? The concept of the hydraulic diameter. So by formula, the diameter is equal to the 4 times area divided by the perimeter. So for example, for a box which has the width, the area is equal to the, for the rectangular area is going to be the W into B, right? And perimeter, which is the sum of all sides, which is equal to the W plus B, then again W side, then the fourth side, which is again B. So the perimeter is equal to 2 plus times the height. So in this, the hydraulic diameter is going to be equal to the 4 times area, which is the 4 into W into B, divided by the twice W plus B. Okay. Now, because we are solving the 2D case, so in the 2D case, the geometry look like in this way. 2D case, so 2D case. So at the inlet, at this end, you can see that okay, this question. What should be the hydraulic diameter? Now see, the height is equal to the small h. Okay. And assume that the third dimension is the 1 here are the unity. So it means that the area is equal to the 1 into h. Okay. The perimeter is equal to the upside, so 1h. And you can go back. If you move in the circular path, okay, you have to pass the full length of the full dimension of the geometry. So if you go upside one time, then you go back again. So it's 2 times of the, so it says h or 2h. Okay, so either 1h or h, and the perimeter is the 2h, and the dimension of the hydraulic diameter is the 4 into area. 4 into area. Area is equal to h divided by the perimeter, which is equal to 2h. Okay. We have the 2 and 4h. So h is cancelled. 2 and 4, the 2 times, so diameter is equal to 2. So the diameter is 2 times, sorry, to the 1 minute. Either h into 4 and it's the 2h. Okay. So 2 to cancel here, so we have the only 2 here. So it's a 2 over here for the diameter. Okay, so diameter is now 2. And from Nernst number we find out the viscosity, because Nernst number is 100, 10,000, which we assume ourselves. Velocity 1 meter per second, diameter 2. So only ring parameter is the viscosity. So viscosity can be solved, and it's equal to the number is equal to the velocity diameter divided by the Reynolds number. So it have to be the 20. Okay. Now we have the some flow parameters, we have some material properties. Now the remaining thing which is over here are the orthogonal, this length and the length of the downstream channel. Okay, this is a bit tricky. Okay, this can be a tricky. Now I want that now you ask questions and then proceed. To the next, I want to ask you questions, that you ask questions to clarify your anything which is unclear. Yes. Perimeter. You want to ask about the perimeter, that what is it is about, or the and question should I proceed further? Is there confusion about this thing? Look in the meter is equal to meter is equal to C. We have the with this dimension. Okay. In the third dimension, assume let's say the 1 meter. So over here. First we talk about the 3D case, okay? We talk about 3D case. So the dimensions are let's say H, okay. Area will be equal to the H square, and diameter will be equal to the H plus H plus H plus equal to the H, and here area will be the H square. So meter will be equal to the 4 times H square divided by the 4. So in the case of the 3D, is going to be the equal to H. Okay. Now the second example is the 2D case. The 2D case, we have the only we have the channel which is equal to the H. The second dimension is not present here. So you can assume that in the third dimension we have the meter depth. Okay. Have the 1 meter depth. So we have the if you solve it, so okay, the area is going to be the should I continue this one?
Yes.
Okay. Okay, next thing is about the the length of the upstream and the downstream channel. This is a bit tricky. Okay, so we should be careful about these parameters. So from the result that the separation point, the flow attachment point is at the 2.7. Okay. So if I to be on safe side, I chose the length as here. So it is just an arbitrary guess, and it may work or sometimes it may not work. Okay. And upstream length is because the flow is developing, so I chose the length of the 5 meters. 5H. So x is equal to 1, so the 5 into 1 is equal to 5. So again I have to choose again I have to decide based on some physical parameters. It depends on basically in the case of pipe. You know theory of pipe that there is region we call this one as the entrance length. Okay, the same is the case with the channel flows. So we have the entrance length here, and after that the flow is fully developed and we have the parabolic velocity profile. So the length should be, on the upstream side should be long enough that the flow is the fully developed flow and the parabolic profile is established. Second is that if you want to shorter, maybe 2 meters, in this you have quite the velocity profile in the parabolic shape by yourself. So then implement that thing with the help of a UDF, which I have in my folder, and I will show you how to compile this one and use that UDF also. So you can even reduce the length from the 5 to the 1 meter. Okay, save your time and your mesh sources. Okay, so if it is good enough, but the downstream length you have to decide based on the Reynolds number. The Reynolds is increasing and you have to increase the downstream, which is equal to this is the LD, or the LD. This length, which is the LU, is good enough, but the LD is maybe short depending on Reynolds number. Reynolds number is increasing, length is and you have to increase this length also. Okay, so you have to decide based on the flow conditions. So from here we have all the geometry conditions. So the small is the 1 meter, this capacity is the 1.9423, this side is the 0.9423, this length is the meter, this downstream length is the meter. So geometry is fixed now, and so fixed the velocity is the 1 meter per second. We can apply the parabolic velocity profile with the help of UDF, which is the user defined function. Obligate condition with the zero pressure, and all the walls they have the zero slip condition. They have the slip condition. Pressure is the atmospheric condition, which is the 101325. Then 1000 and the viscosity is the 20 we have. Okay, now flow is fully defined, parameters are fully defined. Now we can proceed for the solution. Okay, after setting this thing, we solve the problem, and we will solve just now after this slide. So let's discuss about the results. So in the experimental work of this boss, they have the stated length is equal to the 2.70584. Exactly that you are quoting from the paper, the reference one. The length here, this is the point here. And from CFD, from this CFD which I am showing to you here, which I have said, that is in the 2.71. The error is only 0.153%. Low error. So this thing you have to create a very good mesh which resolves the flow in a very efficient and a very effective manner. So I will tell you how to create this mesh and how to solve this problem in the Fluent. Other cases, some other Reynolds numbers. So for example, this first case is the Reynolds number of the point. Limit can be, from my point of view, it depends on your requirements. but mind that the 10% error is in the initial when you are student, as it is 10% is good enough. But it should be less than 10%. This is the starting, we can say this is some sort of some starting error, which should be not more than the 10%. Okay. So from this point of view, this error is very low, 153. 6 not numbers, last case is for not number 100, which we solved now. The cases are for not number 50, then it's a 10, 1, point and the point 0, 0. You can see that the circulation zone or separation zone is very, very low, and this case and this increases with the not number. So it should be the case with your flow. If you solve these cases, I would recommend that you should try these cases and let me know. And maybe you can increase the nonce number to the 200, 300, and let me know that how the solution is varying with this nonce number, and how accurately you are getting solution for your setup. Check it, and I will recommend you some. Maybe I will suggest you some best practices to get some accuracy, more accuracy in your case also. Okay, so I will show you this one on the ICEM CFD directly instead of going through the these slides. These slides are for you for your reference in the future. Once this webinar is over, you will get the video also, but you also will get this thing in the black and white, so that you can refer this one later on. So here in the black and white, I will directly on the ICEM CFD. Search from the start menu, and you can open the ICEM CFD. So this is the ICEM CFD over here. Thing is that we should be knowing the point location, because now it's a choice. So let's say we call this point as a point 1, and we call this one as a 0, 0, 0. So the step height is a 0.9423. So we add this step height in the y direct, in the y coordinate. Second point is that it's a 0x 9423. That is required by the software. That's have to provide. Otherwise, this case, the 2D case, so they don't need to provide a z direction, but it's required by the software. So we are also here in the slide. The third is in the direction, which is the length of the upstream channel is 5 meters. So in the direction, so it's the x is the -5, y 0.9423. Point 4 is in the y direction, and it's the full length of the channel, which is 1.9423. The 1.9423 xm, and this point number 5. Here channel length is the 10. So from this point, this x is equal to 10. And the channel is the 1.9423, the same as the point number 4. The last point is the x value 10, y 0, and the z 0. So these are the values we are going to input inside the ICEM CFD. So we just refer this picture. So in the IFD, just go to the geometry, and the geometry you can see here we have the point option. So just click geometry and then the point option. In the ICEM CFD, we have the control on our meshing, especially the Hagra mesh is the best one in the ICEM CFD. You cannot control the mesh as we control in the ICEM CFD with the meshing. It some features like the map meshing, but it's not good enough. So this is a very simple problem. So you cannot realize the full power of the ICFD. But for very complex geometries, you can only the ICEM CFD Excel. And however, you have the more control on the ICEM CFD grading, which section you want to put the more points and there are more schemes to distribute a number of nodes in the different pages. So this is a very, very, very powerful software. You cannot find this thing in the ANSYS machine. So the price of the software when you will go for some professional work. Okay. Here the XYZ option, the second most option from the left side on the top row. So when you click on the XYZ, other options will open up, and you can. This is a software solution. Our meshing were limited to some specific applications. This is not a general purpose meshing software. The general purpose. It is used for some specific purpose, but it is used for every problem. Whether it's a CFD, it's a heat transfer, it's aerodynamics, it's or you can name it and you can use this software. It's the software of choice for the funny application. Okay. One is the 000. Okay. 0 and 0.9423 and 0. So 0.9423. 35.9423 and 0. So just keep the 0.9423 in the Y and put the X as a -5. Click on apply. Just zoom in so you can see that we have the points over here. You can see the location that you can see the information about the points or any other geometric entity. Whether we are creating the point at the right location or not. So you can click on this option. Then you will see that the coordinates of the point are the 0, 0, 0. Then click to unselect this option. Then again choose the second point with the help of the left mouse button. See, we have the coordinates 0, 9, 4, 2, 3 and 0. Right. Minus 0.9423 and the point 0, which means everything is going. The first point is the -5, 1.9423. So just keep the -5 and change the 0 to the 1.3 and the fourth point. This point is a 10, 1.9423. So just X to the 10. Y is 1.9423 and this point is at the X and the Y 0 and Z 0. So now we have the 6 points here. We have 6 points over here. And with the help of the curve to create enclosed geometry. So to create a curve, the section here. Okay, so click the curve. Then choose the first option, which is to create the curve from the strength from the points. So the first option in the choose the 2 points with the help of the left mouse button. And to confirm the section, you have to click on the middle mouse button. This will create a line. Then again 2 points with the help of the left mouse button and then middle mouse button. Then again choose the 2 points with the help of the mouse button and then press the middle mouse button anywhere inside the. Just keep on doing this thing for the 2 points, the pair of 2 points, and you will be in this way. Okay, so you can compare this one. I think Farooq, you are with us, and you can I think joint aside the right movement, right? So you should not have any difficulty. Farooq, can you hear me? Okay, so created all the these curves. Now the next thing is to create the boundary condition of the parts. So right click on the parts here. Okay, right click on the parts, and the first option you have is the create part. Okay, so basically we want to give the names to the different boundaries. Like we see here, we have the inlet over here. We have the inlet over here. Then we have this upper channel wall blue, then wall S, then the B and the wall top and outlet. So we want to give the names to these boundaries in the ICEM CFD. So right click on the parts and click on the create part. Let's say it's the inlet, and the option create part by selection. Click boundary by help of the left mouse button and then button to and position, which is a wall underscore U. Choose this boundary and again press the middle mouse button to confirm the selection. If you click on the plus sign, you can see the piece parts over here. U. Then we have S. Let's select this boundary, and we have the wall down, wall D, and then we have the wall upper, and we have the outlet R. You can call this one as the out. So name does not make any difference. So this should be the name which should be clear to you, and you can understand this name. For this, please choose option all using computer. Then you'll be able to talk and you can listen us. Then the left side. So we have defined all the boundaries. The next basically create the thing is the blocking link between the mesh and the geometry. So parameters of the mesh on the blocking. When we link this blocking to the geometry, so the mesh will take the shape of geometry, but the parameters we have defined on the blocking and information, everything, all the operations are done on the blocking. And once we link this blocking to the geometry, it will take the shape of that geometry, and it will be their geometry. And when we output this will be for that geometry. So the block shape will always of the block type, which is a cubical. It will have a different mesh shape depending on geometry, which we are going to associate the block. So block is some intermediate thing which you will work on and link it with the geometry. Once you link this one with the geometry, you will get a mesh for that geometry. Okay. So for example, here we have created the block for this geometry. It's in the green color. Geometry is outside over here. And to create the link, we have to associate the blocking with geometry. This is how the blocking works. Let me show you on the ICEM CFD directly. So you go to the blocking option here, and then create block option, the first option in the sub tab over here. So then create block. Put as a fluid. Normally we put the fluid because it's a fluid. You put the name solid also. You can put the name air. You can put the name water. So any name which is easy to understand, it's easy to refer in the future, is good enough. But you should not put the name as a solid because the result for the solid parts which has some heat transfer, but there's no flow inside that thing. So don't put a solid for the anything which is any fluid or the water, maybe air. And from the initialize block side, the option we choose, because the 2D case, we'll choose the 2D option. For 2D case, always choose the 2 dependent option. So click on apply. Okay, you can see we have some error. Okay. This error is always there, and I continuously observe this error. So the solution is simple. Just go to file menu. Just go there. And save project as. Click on this one. Give it directory, so just use the directory which is suitable for you. And save the backward pressing step. Okay, just save it. ICEM CFD, and then go to the E directory, and from here tap on the backward pressing step project file. Then check the edges and then click on the fit to window and create the block. With some problems, and you have to recreate the block. Now this is okay. You can see this is a just fit on the geometry. So turn off the geometry to see the block. Basic simple thing. It's a very rectangular box here. Okay, just a simple box, and it is separate from the geometry which is over here. Okay. So right now there is no link between the blocking and your geometry. The link, and before we have to make the shape of block as the shape of the geometry in a very rough way. So because block cannot be have some curvature, so first thing still block will have the shape of rectangular. So we can split the block. We can have to cut it in a way that it can ultimately represent the geometry under the process. So here you get the window to the front from the view. You see that something is extra, which like over here. It is the part from the blocking. This we have to split block, so just go to third option in this blocking subtab. It's over here, and first option is a split block option. Okay. Yes. Anything which you want to ask? Anything you want to ask? Yes, everything is clear. Okay. The design molder, I can use it, but this is simple geometry. So it will maybe it will use more time because the geometry part was very simple, few points and the curves. The next thing is the blocking, which is basically is the main key of the ICEM CFD, which cannot be done in the initial meshing and design order. You have the other error in the okay, you can close the ICM CFD and then again open it, then again try it. So 2 or 3 tries you can create a block. I don't know why there is some error inside. It's maybe some bug in the ICM CFD 18.1. So I think you can use 18.2 or 17, and I guess there should be no error in all versions. This is error of the version, so cannot do anything about this thing because the bug in the software. Okay, it gives me this there again and again. So I have to close it, open it, then after 2 or 3 tries or 4 tries, this error is gone. I have to try this thing 4 or 5 times, 6 times, 3 times, 2 times. Then it's the block. Okay. Okay. So now we have to make the shape of the geometry. So we can split the block at this position, and from the split method, choose the method as the point. So at point we can choose the point. We want to split the block, and it will precisely split block at this location, and then choose the vertical edge. Okay, and then choose this point. This split the block over here. So now you can see if you go to the blocking and if you click on the block and then click on this solid. See, now we have the 4 blocks. Okay. We are over here 1, 2, 3, 4, and from these 4 blocks the 3 are useful and the 1 is not geometry. So just did this block before moving to the next command. So here we have the option for the block. So you can then just click on the middle mouse button to delete this block from this screen. Now we have the 3 and separately. It's in a very separate. It's combined these 3 blocks. Now we can move to the next command and check the block from here and uncheck the point and curve. You can see the block shape. The 3 are there. You can enter points and the curves again. The next is basically to link between the block and the geometry. The link we create here is known as the associate. As the associate in the ICEM CFD. That is to create a link between the geometry and the block. Create a link between the geometry and the blocking. The link between geometry and the block. These are 2 separate things. Okay, we have the option over here. Here. And associate the 2 things, the text and edges. You can see that we have the 2 main things, which is the geometry. Second thing is the block. For the point which has the no width, the corresponding thing in the block is known as the vertex. And here we have the edge, and then we have the geometry. We have the surface, In the block we have the face. The geometry we have the solid or 3D geometry. In the block we have the block. The block is a 3D thing. Okay. So these things are associated to each other basically by the ICEM CFD. Yes, they are done by ICEM CFD automatically. So you don't have to do this thing yourself. The only which is to be done by yourself is the association of point to vertex or point to the vertices and the edges or edge to the curve or curve. It's done by the so we are with the help of these two options. The thing is to associate the point to the vertex. So make it bigger, this panel. Put the point to the vertex and set done. With the help of the leftmost button, vertex, then point. Vertex, then point. Okay, then just turn off the curve and just check that if the vertices have the color of the red. Yes, the red color, it means that they are associated to the point. See, the vertex has the color of the black. The black vertex. So it's not associated to the any point, but it's associated to the surface. Black color shows that the geometry is associated to the surface, the surface. The red color shows that this vertex is associated to the corresponding point at this location. You can end the points and curves again. The next thing is to associate the edge to the curve. So select the edge over here and press the middle mouse button to confirm selection for the edge, and then select the curve and then press the middle mouse button. I'll select the edge with the help of the left mouse button, then press the middle mouse button. Again with the help of the left mouse button, select the curve and then press the button. Similarly over here. Okay, here we will choose the two edges because the two edges are corresponding to the one curve. With one row, then this curve. Okay, so on the top side we will choose the two edges, this one and this curve. And the sign that the edges are connected to the corresponding curves, then will turn off the curve and point. If the color of the edges is the green, it means they are associated to the corresponding curve here. Okay. Turn on the again curve and the points. You can file also. Next thing is to provide the mesh information. So we have to put the number of nodes on the each edge. Okay. So we will use the pre-mesh parameters option and the edge mesh parameter, the third option from the left side. So here I will provide number of nodes to 40. By geometry is the default here. This one I will keep it at 0.005 because I found out is good enough, and the ratio is 1:2 or 1.1. Is again 0.005 and the ratio is 1.15. Apply. Don't forget to enable the copy parameters to all parallel edges and click apply. So this will copy these parameters to all the edges which are parallel to this. Acceleration is done. You can see the recording, but the acceleration is done to create the link between the geometry. You can see the the video recording, or you can discuss this thing at the end of this webinar. Okay, so I can continue this one, and at the end of this session, I will again the session thing or any question you have. Okay. On this side, on the digits, we put the number of nodes is equal to all 40. So I will not decide anything over here, just the number of nodes. Okay. Then here I will put the number of nodes to the 40. Okay. As I told you in the starting, that problem, because luckily I know the solution. So I told you that the flow is experimentally the flow at created point is at the point 27.084. So tendency to put more nodes which has a resaturation zone. So I think the idea I have is to split block into the more parts. Just have the more fine mesh in the region where we have the resaturation zone or the separation zone. That thing I just split the block at the location. Select. I will choose any location on this horizontal edge and split the block. But whether go to view and click on the front. But I don't know that this length of this one is 2.78 or 3 or 2. So I don't have any idea. Okay. So now to confirm that this length is not less than 2.7, otherwise there is no benefit of making this block. I need to change the size of this block. So I have the option over here. Okay, vertices. So based on this one, I can exactly set that this length should be equal to the 3 meters. Okay, with the 2.78 I have the saturation zone, like and region here. I can very nicely capture this saturation zone, and I have the very accurately the reattachment point also in my CFD. So this is the way I use the blocking. So this is the power of the blocking, because I don't need to put the geometry at location or to create the points and then create the faces and then create the map meshing method. I just put one split over here and all everything done. So confirm that the size is on. So from the move vertices command, the last option is about the edge, this one. Okay, so I will choose this option. Then edge or edges. So this edge is a 3 to 4. So okay, so this is bigger than what I thought previously. So I thought it's a less than 3, but it's a bigger than 3. So I just want to make these 3 edges equal to the 3. Just and 3. But I don't want to move these vertices towards this direction. Okay, maybe direction. Okay, these points are fixed because these are expected to the they cannot move it, but if we can move this point both ends. So instead I will freeze this point. So I have the option there, the freeze vertices, and choose these 3 vertices in the block and apply. The length of edge is exactly 3 meters. Okay. We have exactly 3 meter length, and we'll put the 40 nodes just in this region. Maybe the next mesh I will put the more nodes also, but this for the first mesh this is good enough. Then here I have the nodes. And then just click on the pre-mesh to see that how mesh look like. Okay, mesh like this. So we have to make some refines in the mesh so that it should look like some professional mesh. So I will go to the pre-mesh parameters here. And I copy all parallel edges, yes, and then on the pre-mesh and then recompute. Okay, looks like a nice mesh here. Okay, now on this edge, what I want to try to get is that the mesh should be on this cell should be of the perfectly square shape. So on the size should be of the same. So copy the size from this edge to the adjacent edges. This option, which is the mesh spacing. So to reference edge as this one, okay, and target edge as this one. This time again the edge is the same, but now the target edge is this one. The same reference edge and then this one as a target edge. Okay, then again go back to the edge parameter and choose this edge. Now you can see that the spacing is set to the point 0.05. Now just put ratio is equal to 1.2 and click on apply. See this second edge ratio is equal to 1.5. Here where you 1.2 here you see the spacing. If the thing to then you have to put the ratio is the 1.2 in the ratio. The spacing 1 is the 0.005 and ratio is the 1.2. There is last one. Spacing 2 is the 1.5. With this, so the ratio is the 1.2. Right click mesh and recompute. So it's done. Okay, thing is on this one because this is the full zone which we have the saturation. So it should be geometric mesh. So what I will do is that I will also put the 0.005 on the spacing 1 and the ratio as the 1.1. Okay, and here is also 1.1. And on the pre-mesh, right click and recompute. Okay. You can see here that the spacing here is very small and is very large. It will not be like that. Otherwise, you will have the error. So I'll do the mesh spacing, and here we will use the spacing 1 is now 0.11. Keep the ratio is equal to 1.2 and click apply. And pre-mesh and recompute. Now the mesh which looks like a professional mesh, and this is what we can start with as the initial mesh, or we call this one as a coarse mesh, and we can start with this mesh to our the Fluent version. Okay. The next thing is to convert this mesh into unstructured mesh. So right on pre-mesh and then convert to the unstructured mesh. Then go to the output mesh and to the solver as a print. In the dimensions, in the edges, for inlet put the velocity inlet, boundary condition, for the outlet, put pressure outlet, for walls, for the walls, so you can copy this condition and then you can paste on the condition which has the same boundary type. You can shift so that you can have the right mesh, you can recompute, and then you can again come to the uncheck the stress mesh here. Check upon and then again uncheck to give these extra blocks on the outside the mesh. You can go to the view and you can click on the front. Okay, the last step in the ICEM CFD is write solution file. So click on next file, click on Okay, the important thing is that the mesh is 2D, so just select the 2D here, and file name, I can choose that it's step, and the mesh is a coarse, it's a very coarse mesh. Okay, we have no errors here, otherwise if there were any errors, it would have been shown over here. Okay, I just want to know that the size of the mesh. So pre-mesh and then click on pre-mesh info. The numbers are approximately 6,221. Okay. So now you can close the ICEM CFD. This is the end of the ICEM CFD. And we will open it from the start menu. Okay, to the 2D, double precision. Here, choose the location of the mesh file to each directory. Go to the file and then read mesh. The file we have just exported, which is a packet coarse mesh. Display this. To zoom the mesh, you can fit the mesh from this command. Zoom any part, you can use this option. You can change the frame. There is the Fluent. Okay, you can fit a mesh to the window. Okay. So thing is given in the this step-by-step tutorial. You can refer this one if you have any confusion. These are all things we have done right now. It's given over here. Okay, important thing is the model is the turbulence model. We have the laminar flow. Okay. Check, don't change it. It's the default. It's a laminar. And just change the properties. Don't change the name of the material as keep it air. It does not make any difference. Just change the properties. So the density is 1000 and viscosity 20. Is the same. We started with that thing, that how to define the geometry or boundary condition of the material. So density is equal to the 1000 and viscosity is calculated from the non-summer formula, the 20. So we just here. Okay. Okay, just click on create to implement these conditions. In the conditions, the only thing we need to provide is the inlet condition, and just put the velocity as a 1 meter per second. The thing is the solution changes. And the control in the control number is equal to the 20. We follow the case up to the required number of iterations. The 1000 iteration is the solution convergence criteria is met, then the solution will stop. So we don't stop solution with this criteria. We want to solution when the number of iterations are completed. Okay. This is just to ensure that we have the solution is fully converged. Okay. This may be overkill, but I want to make sure the solution is fully converged. Okay. The next thing is to initialize the solution. So just click on Initialize and method. Let's next thing in the run calculation, I will just put the number of iterations to just 1000 and click for the solution to converge. It will converge. It will basically converge to a very low value, but it will only stop when the number of iterations are 1000. Now, right now it's at 350 or 360, 370, 80, 390, and very to the very low values of the residuals, -8, -10. Applying the right now I'm not applying the velocity profile. The solution is complete. Okay, the next thing is to get the different parameters. We can plot the velocity contours from the go to post processing the contours and edit. Build. Yes, it's converged. It's fully converged. So we have the pressure over here. You can click on the velocity. Actually, I cannot be 100% sure, but because I have run this case for too many iterations, because you can see that the continuity equation is converged to -14, item equation -16, -17, and you require that the solution should converge to the 10 power -4 or -5 is a very convergence. So very low values in the convergence. I'm certain about that I have the converged solution. The usual convergence criteria is 10 power -4 and it's very low value here. Okay, but we check results that if in this case for the right, yes, if you run this one for more iterations, you can see that thing. But now it's the residuals are going to be they are going to be displayed. They are getting okay. The lines are straight. Okay. So they plot the vectors. Let's see the vectors over here. So you can change scale to the 10. So you can see how the vectors are there. You can see the reverse flow over here. I can choose the in-plane and fixed length. And put the scale as a 0.01. It depends on the how it will work. So you can change as you want. So you can we have the separation zone over here. And after that the flow is attached at this location. Our flow is separated. So we can say that this is the location of the flow element. So we need to find out the length of this dimension. what happens in the separation? It's a very important thing to know. What happens in the boundary layer is when there is separation, the separation boundary layer will look like this. Okay. At the point of separation, this have some negative flow, and once the flow is reversed, we have the negative velocity, and we have the negative shear stress. Okay, the separation we have a zero shear stress. Here positive shear stress because the shear stress is equal to viscosity and the partial u by partial y. It's a positive when the slope is positive. When the slope is negative, like this, the shear also is a negative. And at the location of the separation, when the flow is separating, over here the shear stress is just zero. Slope is zero over here. The point where the slope is zero with the separation point. So, and when the shear stress is zero, then the negative means we have the separation zone, and when positive means the flow is attached. So this is how we judge the flow when it was reattaching, when the flow is separating. So check the shear stress. Shear stress is basically the magnitude. So for example, if the shear stress is behaving like this, for example, if we have the positive value here and the downside with negative value, so this is the point of when the flow is attached. Here flow is separated, attached. This is a point of separation or point of reattachment. You can see if you are coming from this side, this one is the point of the separation. If you are coming from this side, because this one is the point of reattachment. Because we are coming from this side, that's why we call this one as the point of the reattachment. The point where the x shear as a negative, as a zero. Okay. Talk about the just magnitude. So what will happen with if you draw the two graphs? This is the x shear stress. This value is the then zero, point of reattachment, then again the positive. In the case of the magnitude of the shear stress, what is that? We have some values like this, then again because these negative values are also being converted into positive values, because magnitude means that we will make the square, then we take the under root. So it will again makes a positive value. Again, look for the mini point, the zero value. Okay. This is we determine the location of the separation or location of the reattachment. So how we do in the Fluent, I will tell you now. But the thing is that we can check the separation with the help of the shear graph. Okay. So we will get the XY plot, and here I will choose the wall stress. Yes, but I will change this one to the X wall shear stress, and I will select the wall. Okay. If I choose the value of the wall shear stress, I will see the values are positive, and flow is attaching. I can go for the X shear stress, and here the value is 0, but this should be after this way 0. So this is the point where the flow is attaching. So just output of the X shear stress as file format, and it's the X shear and the backward facing. And open this file in the so here Click. Okay, and then import the this data file from there. Just locate the file which we have saved here in the E file. The file over here. Finish. Okay. Okay. So if you start from 0, you see we have the some value, something 0 value over here. Okay. So this is value because this is the location where the flow is starting. So this is the location over here. If I check the mesh, you see this is over this region. This is not important for us. We have the separation of the flow. It's a known fact, but we want to know where the flow is attaching. Okay, so it should be somewhere at some value like a 2 point something. So I will go for the 0 value and so we don't exactly the value of this, but we should be between these 2 points. Okay, minus 1.294. All right. So you can interpolate between these 2 points. So it should be like 1.21, 1.94. So we say okay, say all in between these 2 points, towards the 2.77. So it's let's say without interpolation, I can say okay, it's a 2.7. So you can see that the 2.7 is there. If you exactly interpolate this value, you can exactly find out that what's the value of the this. So you can see that the solution problem is we know from the experimental data this was is around 2.74. Okay. So in this way, okay, if you want to create a more accurate solution, the location, then you have to put the more nodes on this in the mesh so that you can have the value location of the where the chest is. So we can find out exactly this location. So if you have more nodes in the mesh, you can have the more in the result. So you can have the more nodes in between and even more locations, and exactly find out the value of the where we have the separation. Okay. So you can quote this value and then you can put over here and you can see okay we have the solution which will be very accurate. Okay, but actually this mesh was coarse, but we also solved this case. These are basically from the fine mesh. We have also put inside this folder which here. So it's the 2 folders. This is for the coarse mesh and second is for the so we have the coarse mesh, Fluent and ICEM CFD files, and also we have for the fine mesh, Fluent and ICEM CFD files. In this case, and how the results are varying with the fine mesh and with the coarse mesh, and all about the today's question. And I will be glad to answer you. questions? Okay, so now we come to the end of the webinar. If you have any questions, you can ask me. If you have any question right now, you can see the then you can email me your questions. Anything you want to ask? Okay, the video will be uploaded on the website and you will get a link on the WebEx. Okay. Okay, so you will get the link. Also, I will email you the links of this file.